All right. Well, we're doing great. We have plenty of time then for our invited speaker here. So we have David from Zoo Inc. joining us from Cambridge, right?
Yep,
Um,
correct.
and David's a lead software developer at Zoo Inc. and formerly spent a lot of time at ARM. At Zoo Inc., they're doing some impressive work doing software for hardware design, really kind of re-envisioning mechanical CAD, building on glTF, and they have a pull request open for extensions to do things like solid surfaces and VREPs. And it's, I find it really interesting because over the years, glTF has always been interested in implicit surfaces and the kind of trade-offs there for the size versus runtime compute. And then seeing it, potentially going to new markets is really cool. So, David, we're happy to have you here and looking forward to your talk. So I'll stop sharing the screen and you could share your slides.
Okay, yeah, well, thanks for the great intro. Hi, everyone. I'm David. As Patrick mentioned, I'm working on the file format infrastructure at Zoo, which is a startup company. I also happen to be the author of a popular Rust library for working with glTF. And Patrick invited me to talk to you about the glTF extension that we're working on, which is intended to expand its use cases in the hardware design and manufacturing industries. So first of all, I wanted to just introduce the company and to give context on what we're trying to achieve. So Zoo is focused on creating CAD software that can take advantage of today's highly parallel hardware that can be easily automated and that ultimately bridges the gap between hardware and software design. We describe our software as, quote, code first in a similar way to projects such as OpenSCAD. This brings benefits such as having differable version control into the CAD world. We provide a remotely executed CAD API service, with the idea being that anyone can create a CAD application on top of our kernel and that they pay for only what they use. On top of this design API, we also have our own code and mouse pointer modeling app. It's a hybrid modeling app. I have to mess around with the settings here because I couldn't change them. They're embedded. But this is what's on show here. The company was established mainly out of frustration of its founders. They had run their own companies in hardware and mechanical engineering. And during the time, they faced lots of problems which they felt had long been solved by software engineers. Moreover, these problems has persisted long enough that there's a general consensus among mechanical engineers that they've kind of like accepted their fate, so to speak, not knowing or believing how things could possibly be any better. So Zoo exists to challenge this notion and to bridge the world of hardware and software design, providing solutions to these long-standing problems. So this begs the question, what are these problems exactly? So in no particular order, I note four of the main issues. The first one is manual processes being very common, particularly when going between CAD applications. For example, one might want to take a part created in one program and perform analysis in another program. To do that require a lot of steps. We have exporting, importing, setting material properties, fixing up any geometry, other configuration, and all this sort of stuff. Another example would be filleting, adding fillets to the edges of an object so that it's rounded and not sharp. Typically, this needs to be done every time the geometry changes, which is a rather repetitive task, quite tedious as part scale. One of the founders told me either a funny story or a sad story, depending how you look at it, about an intern at one of his previous companies who was given the sole task of filleting for their entire tenure at the company. That's just how much time it takes. The second is the fact that a lot of CAD software is slow, to put it bluntly. Editing complex parts, assemblies, and drawings is often a painstakingly slow user experience on an ordinary workstation. This is assuming that software hasn't already crashed, which is also a common occurrence. What this does is it pushes high system requirements onto the burden of seasoned mechanical engineers. The third one is the cost of licensing of an industry standard CAD application today. Even for a single user, this is likely to be steep. We're talking like thousands of dollars for a license for a single person. For startup companies getting into this industry, this is quite a high barrier for entry, perhaps requiring several licenses for all their team members. And finally, we have problems with interoperability when sharing CAD data between applications, and particularly with manufacturers. The need to repair models after import is not an uncommon situation because each bit of software has its own quirks. For example, different formats might be interpreted slightly differently in different CAD software, and that leads to like manual intervention. So this leads me on to the next topic, which I call the CAD format minefield. When choosing a format to export from a CAD program, there are lots of options. On the slide here, I picked what I would consider the most common ones today. In reality, there are far more than this, and you could easily find like 10 more to add to this slide if you tried. When it comes to choosing a format, each one will have a trade-off between being lossless, exhibiting good performance, and being vendor neutral. So if I start by talking about the proprietary formats, these naturally are the ones that will be least lossy. However, they cause compatibility issues for their recipients. For example, if I were to send a SolidWorks part file from one version of SolidWorks to a manufacturer that uses a different version of SolidWorks, then that manufacturer might require an additional license to be able to work with that file. If the customer was using a newer version of the manufacturer, then the manufacturer might not be able to work with it at all, and the customer would have to resort to using some other format which is lossy. Now, this is an expensive and undesirable situation that obviously we want to avoid. So over the years, various vendor neutral formats were developed to avoid these kinds of situations. Vendor neutral formats, they're not completely lossless, but they retain enough information to be useful in most cases. Now, the two most common formats in this category today are the IGES standard, which was first published in 1980, and the STEP standard, which is from ISO, it's ISO 10303. That was first published in 1994. So they're both quite old formats. Having said that, however, STEP does still receive regular updates every year or so. At the end of the spectrum, we have the abundant choice of mesh formats. These formats tend to be the most straightforward to process. And by straightforward, I don't necessarily mean fast, but rather simple to add support for. The problem with these formats is that they lose almost all the information contained in the original authoring file. They are, however, used commonly in 3D printing and in finite element analysis workflows. Of all these formats, none of them fit into what I would claim is the ideal zone, which would be a format, well, the zone which contains a format that is lossless, vendor neutral, and fast to work with. With some tweaks, I think that glTF could be a contender to fit within this space. Now, of course, it would be naive for me to talk about any of this without first mentioning the N+1 standards dilemma. Given this is a standards forum, I'm sure you're familiar with this particular comic already. I added this slide because I wanted to make a point that we're not necessarily trying to invent a new CAD file format, but rather we're trying to improve upon one which has already found uses and gaining traction in manufacturing sectors such as 3D printing, that being glTF. So what I'm really presenting to you is the case for glTF for CAD. As it is today, there are many advantages to using glTF over other mesh formats. I'm sure I don't need to go into much detail because I'd be preaching to the choir, so to speak. There are, however, some noteworthy things that I wanted to point out because they might not be so obvious. The first is the fact that it's a hybrid JSON and binary blob structure. Most other CAD formats are either binary and proprietary, or they're neutral and text-based with low information density. What's great about this particular representation is that it allows for both large amounts of, quote, dumb data with minimal processing, as well as structured data that can be processed or discarded as required. Also, because it's JSON, it also benefits from years of optimizations from web technology. The second detail is something I expect people don't think about very much. It's the fact that glTF standardizes on its units and coordinate system. There aren't many mesh formats that have this provision. And this leads to problems such as objects being the wrong size, where different units are being used by different applications, or the wrong way up because it's facing the wrong way because different coordinate systems being used. In these situations, the user would typically have to manually intervene, whereas glTF solves this problem without any modification. The open nature of the specification is great for industry collaboration and adoption. If I were to propose changes to STEP, for example, I wouldn't know how to go about that. Whereas in glTF, I can just open a pull request. Also, obtaining a copy of the STEP specification is neither free nor inexpensive. With glTF, it's royalty-free. Finally, the extras members of the glTF data structures means that users can package all sorts of data in one file, opposed to having lots of ancillary files all over the place. We can embed things like manufacturing data, bill of materials, etc., all within one CAD file. Moving on, that being said, whilst meshes, they're great for GPU rendering, they are discrete objects, and so they can only approximate smooth solids and surfaces. CAD applications, on the other hand, they need to know about solids and surfaces much more precisely. In particular, they need to know, they also need to know how surfaces are connected to one another. The industry standard method for expressing solids is a combination of parametric curves and surfaces bound to a graph data structure. The curves and surfaces describe the geometry of the material boundary, and the graph data structure describes the solid's topology. This combination is known as boundary representation, or BREP for short, and our proposal is an extension to glTF that would supplement existing mesh data with this boundary representation data. Now, as it's a supplement, regular glTF renderers wouldn't need to process the extension at all. However, if desired, the geometric and topological data would be available for use. On the flip side, you see it from the other point of view, CAD applications would be able to render the BREP almost immediately using the provided mesh, and this removes the need for a time-consuming and complicated tessellation step. Plus, as an added bonus, it benefits from all the nice PBR materials glTF has. So the eventual goal of this extension is to open up glTF to more use cases in the hardware design and manufacturing industries. For example, with BREP, it would be possible to use a glTF model in a mated CAD assembly. It would also allow for analysis and rendering software to perform their duties at an arbitrary level of detail. So what's in the proposal? We have three main concepts to consider. The first is geometric primitives. These are new objects that describe the origin of meshes. That is what the surface would have looked like before it was discretized into lots of polygons. Now, NURBs are included in the proposal, which provide the most general case of curve and surface. This is great because practically all manifold solids can be expressed using NURBS, including spheres, cylinders, tori, etc. We do, however, include specific elementary geometric types such as planes, spheres, cylinders, because it makes the processing much more efficient that way. Secondly, we have topological primitives. These tell CAD applications about the local neighbourhood of each face and its seams. One application of this data is to help tessellators resolve accuracy problems at the seam where two faces meet. One key difference between BREP and meshes is that this topological data allows faces to have holes. On a face, this would be represented by something called an inner loop. I'm not sure if you can see my mouse cursor, but this is what I'm alluding to here. And in a similar sense, solids are permitted to have empty regions, which are called voids. Finally, we have 2D trace curves. Now, different standards give these curves different names. We've chosen trace as a neutral name and to give a clue of what they actually are. Other standards might call them trims or co-edges or something else, or P-curves or something. What these are curves are 2D curves in the parameter space of a surface that will match a 3D curve. It's best explained with an example, like in this diagram here. On the left, we have this flat rectangular face with a circle cut out of it. This circle will be represented by a curve in 3D world space. And on the right, we have the exact same circle, but instead represented by a 2D curve across the planar surface of that face. And again, this is useful for analysis and tessellation and stuff. So those are the three main concepts. In terms of interoperability, the aspirational goal of the extension is to be an eventual drop-in replacement for STEP. With that in mind, the data structures have been designed to be trivially convertible to and from their representation in STEP. Of course, there's much more data in STEP to be captured than just the BREP information, but these can be left for a future development. One thing we've also considered is USD interoperability. Now, as far as I know, USD doesn't have BREPs. It does, however, have NURBS patches and elementary geometric primitives. All of the information in the extension could be mapped to USD geometry or NURBS primitives by a file format plugin or otherwise. The extension also pairs well with this new mesh manifold extension, which is also aimed at the CAD industry to specify manifold, which is colloquially known as multi-type mesh geometry, and other areas of the core glTF specifications, such as animations and materials. Okay, so to wrap up, I have a few sample modules to show off for you, 7 in total. In the next few slides, what you'll see is on the left-hand side will be a glTF file containing a tessellation and BREP information, and it's visualized in Don McCurdy's glTF viewer because it shows, like, you can show the wireframe and stuff. On the right is the same glTF file after being converted to STEP and then loaded into another CAD program. So in other words, the BREP information contained in the glTF file visualized in another program. I've used FreeCAD. Okay, so this first model is a handwritten model. I call it bagel slice. It's a toroidal surface cut in half. So it demonstrates toroidal and circle curves. And the title says it was made to investigate a particular bug I had. The second one is a file that was a bracket rather that was designed in our own modeling app. What it's demonstrating are cylindrical surfaces, both in the fillets at the edge here and also the holes in the faces. That, in other words, the inner loops of the faces. Next up is a file that was given to me by a coworker. This is a file generated from another CAD program, and that is been passed through our converter to glTF on the left and then back to STEP on the right. It just demonstrates a more complicated part, and we thought it looked cool, so it made the presentation. The next couple of models, they're all generated by our text-to-CAD API. This one was generated with the prompt involutes helical gear with 36 teeth. What it demonstrates is NURBS curves and surfaces in our BREP format, and again on the left, the tessellation of that. Now we have a dodecahedron that represents just a really simple object with simple plane of surfaces and line curves, something other than an extruded solid. The penultimate one is generic unbranded 2x4 toy brick. Again, it's just representing cylindrical surfaces, both extruded and cut into other surfaces. And finally, we have this snowman. I was quite impressed that it actually produced something. The text-to-CAD tool for this is a CAD model of a snowman demonstrating spherical surfaces. And that's all. So thank you very much for your attention and listening. I'd love to hear your comments and criticism, either on the pull request or alternative, you can send us an email. We also have a Discord chat. That's the end of my presentation. Does anyone have any questions?
David, that was really, really fantastic. It looked very well presented, clearly well researched. Thank you for that. I have a feeling we're gonna have a lot of discussion. Aaron, are you turning on your camera to go first?
Sure. Yeah, this is great. Good stuff, David. I'm curious, like you mentioned a lot of really interesting use cases up front for like filleting and things like that. Do you think there's a role for USD to play there where you could have like a baseline glTF for your solids and then have USD sort of doing incremental edits atop of baseline for things like that?
Yeah, absolutely, especially when it comes to like the NURB surfaces. However, it doesn't matter. It would be lossy at the moment because USD doesn't have the BREP information.
Right. Yeah.
But certainly all the geometry. Yeah, absolutely.
But certainly a lot of the sort of data models that you're introducing into glTF could potentially be mapped to USD schemas and
Yes.
things like that. Yeah. Very cool.
Thanks.
Cool. Yeah, good question. I see Ed has a question too.
Yeah. So you talked about, I think you called them trace curves that provide an additional 2D mapping. Does that translate to? I see U and V there, so I'm thinking UV coordinates. Does that allow like textured materials to be applied to these meshes, even the even the parameter space meshes, and not just the vertex meshes?
Yes, that's certainly the case. The tessellator, our tessellation algorithm at the moment does actually provide the UV coordinates as texture coordinates.
Yeah, so you could have full PBR materials then.
Yeah, absolutely.
On a model like that. That's very cool. Thank you.
Dan, did you have a question?
I guess it's not so much a question, but what I think is most interesting about it, it sort of provides a very concrete use case for why to put BREPs into glTF. I mean, I see that as kind of the, in some sense, most interesting aspect of it. I'm a little concerned, and then as far as like your requirements, David, it's not clear to me if glTF is robust enough in carrying along the kind of metadata that CAD systems usually carry along, which is a lot, typically.
True.
Anyway.
That's true. But if you consider an average step file, that we get, that's really kind of what we're looking at. I think most data that can be represented in the step file could be transferred over to glTF.
Mm-hmm.
But you're right, there is an awful lot of data that CAD files typically have.
Yeah, Sandy, maybe that's a longer term investigation, but just the initial geometric work here, it looks like maybe it alone could add value.
Mm-hmm. Oh yeah, absolutely.
So Neil has a question.
Yeah. Firstly, thank you, David. That was an awesome presentation. I really like the way you kind of partitioned this up. As we were talking about this at 3D Formats call earlier this morning, we were noting that adding complexity into the base specification glTF is probably hard to do because, of course, not everyone using glTF is going to need to use it in the CAD space. But I really like the way that you've kind of positioned it as extra data that can be ignored if you don't need it. I mean, that kind of opens up the possibilities. So do you imagine it as putting this metadata or extra BREP or other CAD information into the glTF file, or would you have it as a sidecar file so folks who don't need it don't have to download it just to throw it away? My apologies,
Right,
it's probably in the RFP, but I haven't I didn't get to that other detail.
That's a good point. I mean, I must admit I hadn't considered that. Yes, it is true. I mean, if you've got all this, it seems a bit of a waste to have all this BREP data and then not use it. It's just it's a waste, isn't it, of space and download time, etc. The way we have it at the moment is it's attached to nodes alongside meshes, and at the root, it's embedded in the JSON at the moment. Now,
Right.
I don't think that's ideal. I've put it in the JSON mainly for ease of prototyping. I think ideally we'd probably want it to be binary, because it would make things faster, and then you have that advantage of you can just skip that binary file if you don't need it.
Right.
Yeah.
And this is a question because I'm not a CAD person. Does all the BREP and the associated information, is it typically, I mean, how does it compare typically to kind of the mesh data size? I mean, are we talking like a small percentage? So it actually wouldn't matter if you downloaded it, or is it a significant size typically?
Oh, it depends. It really depends. And it's an interesting question because the mesh data, there's a few packets of large data, whereas BREP, it's the other way around. It's many packages of tiny little bits of data. I think for a mesh with lots of curves, solid with lots of curves and intricacies, the mesh data will be larger because there's so many triangles. However, if we're talking like really simple things, then the BREP would be larger because they're so, like if you're just dealing with like planar objects, then all of the lines and the plane surfaces, they're quite verbose.
Right. Okay. So it can be big. So the size is a concern. So binary. As you say.
Yeah.
Avoiding download maybe is a worthwhile thing to consider.
Yeah, it's something I've considered. I paid a lot of attention to try and certainly things that occur very often, like references, to try and make them as small as possible.
Yeah.
I went so as far as to try and to introduce like a negative index, but it turned out to not be a good idea.
Shall we go over to Ashwin?
Yeah, really awesome extension proposal. I love it. And, it opens up the doors for things like LODs and, you can do really cool things with this. I had a question about your thoughts on, do you think for interop purposes, the tolerance factor would be something that should be embedded in the extension where, here is my beer app and this is the tolerance we need to maintain so that we get good parity between different CAD applications. Any thoughts on your side?
Yes, that's a great question. The answer, absolutely, yeah. GD&T, right? I think is the industry geometric distancing and tolerances or something like that. Yes. However, at the moment, I'm just focusing on the geometry and the topology, but there's definitely something that is very important and needs to go in there, right?
So these examples that you shared are with your viewers, but let's say we had to update 3JS or existing browsers, existing glTF viewers, they would have to have some sort of a kernel that handles this, right?
Well, for viewers, the idea of it being supplementary is that they don't have to tessellate it at all. It's got all the rendering, it's got all the information they need to render without doing anything. They can just totally ignore it. Where the BREP information comes in handy is supposing a customer exports a file, let's say a mesh file, and sends it to like a 3D printer manufacturer or something, and then the 3D manufacturer wants to send the file to some other company. They've lost all of that BREP information at that point, so they have to go back to the customer to ask for it. Whereas when you have it together, you can do what you like with it. You have the best of both worlds.
Got it. Yeah, that makes sense. Thank you.
So David, do you think, is there a future where, if a lot of folks in manufacturing would start using this glTF extension, that, there's the mesh data plus your extension for, say, the implicit surfaces that could be concise. Do you think they would ever start maybe using low-res meshes just to keep the payload size down as the industry starts to adopt being able to, to read that supplement information to then, tessellate on the client?
Yeah, I mean, absolutely. Yeah, that seems quite logical. In fact, I'm kind of debating whether it would be acceptable to have it as a standalone extension too, so that you don't have to provide the mesh, but with the provision that you have to put in the extensions required. So you have to say that this is a required extension. And therefore, you can remove the mesh to save some space, but then it pushes the burden of tessellation onto the user. And that's where the tolerancing, as Ashwin, I believe, pointed out, that's where the tolerancing becomes very useful.
I think that's a conversation worth having. I don't know the answer to it, but I think that's definitely something to talk about. Other questions or comments for David?
Quick question. You provide both 2D and 3D curves in your presentation? Yeah.
Yes.
And looks like all the periodic surfaces have been splitted, no? Once converted to BREP.
No, this is just one example, but there are provision for closed faces. Our original snowman model.
Yeah.
In our original snowman model, I actually generated this one recently, but the first one it came up with, it was actually separate spheres, which is not great because of it's not manifold, but there were all closed faces, is what I'm trying to say.
Neil?
Yeah, this is really interesting. And this isn't a loaded question. I'm not trying to push your answer one way or the other. If we were to do something like this, do you see this complementing step that would continue to evolve and be widely used, or did you see it incrementally, not any, incrementally replacing step? Again, it's not a loaded question. I'm just trying to kind of figure out what your mindset is.
Yeah, I mean, I think they say it's up to the industry what they want to adopt, but
Right.
I mean, as I think I mentioned like the aspirational goal is, yeah, I mean, it'd be nice to have like a modern replacement to STEP,
Right.
something that is a little bit more information dense, that
Right.
can be parsed perhaps in parallel, requires much less processing. I'm not sure how familiar you are with STEP, but there's a lot of things that make it hard to a process like forward and backward references and stuff. It's,
Right.
Yeah.
So you wouldn't, Sandy. I mean, Sandy, go ahead. You know a lot more about this than I do.
There's no way glTF is going to be a replacement for quote unquote STEP. STEP, I was just looking at some old stuff, there's something called Part 21. That's the geometry file format portion of STEP.
Right.
There's a gazillion other things like actual mechanical tolerances, feature representations. There's a lot of other stuff. I mean, I think it would be a good way to, let's say, maybe glTF would be a good standard visualization format for Part 21.
Right.
That would make sense. But
that's true. But most exporters don't provide everything in
right.
that particular thing. I think there's an agreed subset.
I do want to mention, I posted in a link to some file analyzer, visualizer, a strange little tool from NIST. But what's interesting, the tool's good, but what's interesting is on that page, there's a lot of other pointers to STEP resources. And it's a good page of just information. That's all. Sorry.
Thanks.
Yeah, I agree. So, I mean, STEP is so widely used, it's going to be here for at least another century, right?
Sure.
So I guess a better way to ask the question is, if we were to do something like this, how can we complement and not conflict and compete with STEP?
Right. Okay. I see your point of view. Right. I don't know if I have an answer, to be honest.
Well, I mean, so why not just, why not bundle both glTF and STEP together, and then instead of recreating what STEP does in glTF, you kind of just reference between the two?
Yeah, that could be an option.
I would also suggest figure out which STEP, again, it's huge. I would figure out which specific area of STEP matches up with this. It's probably the people that were involved with the geometry representation, and talk to them. I mean, I could figure out how to make that connection. There's a lot of people at NIST that work on STEP. But
it's interesting you say that. You said it's huge. That's part of the problem, really.
Yeah.
It's so huge that every bit of software interprets STEP differently and has its own quirks. It supports some things, doesn't support others. By being very specific and picking like the bits that really matter, it removes a lot of ambiguity and potential for differences.
You're 100% correct. But what STEP did is they broke the standard up into a large set of profiles, and it's the profiles that people really work with.
Yes.
You mentioned the AP, the part 42, but this has lots of application protocols. So this seems more closer to AP 203, you know, the control design.
I think 242 is like the latest like one that everyone
Yeah.
uses.
They use it's more common.
Right, and then just for normal standards people, an AP is a profile.
When STEP is so huge, does STEP also provide like PBR declarations, like texture associations? Can it handle really photorealistic digital twins?
Not that I know of, but
I don't believe so.
I wouldn't put it past them to add something like that.
And there's probably no interest in the CAD community to present the final product properly.
I'm sorry. Sorry, Tom? Is that as a question? I didn't understand.
Yeah. Then I think probably the CAD industry is not interested in presenting the CAD products photorealistically.
No, that's not. I don't think that's the case. There are lots and lots of programs. A lot of them are quite specialized, specifically rendering parts and photorealistically.
And
not based on the step files, because they don't have
based on step,
the data. Yeah.
No, but when you get to like architecture visualization, which is very similar to CAD stuff, they very much care about how things look.
Mm-hmm.
Thank you.
So Sandy, are you aware of any conversation between the STEP community and the glTF community?
No. But I'm not really involved in the STEP world anymore. I could find out. I don't.
You think it would be worth exploring, maybe?
Yeah, I could find out. It wouldn't be too. It shouldn't be too difficult. I don't.
Because it would be better for everyone, right? If we can, if we discovered we had a constructive conversation with the STEP community, and we had agreement on where either glTF or USD can add value and enable different community uses, not just go.
Yeah, I'll find out where the connection, if it exists, and if not, what the right connection is.
I mean, Guy or Eric, I mean, has USD, I know some of this is something that USD has been talking about. Has USD reached out to the STEP community already? Do you know?
Not that I'm aware of. There is BREP work going on in potential new working groups, and potential new working group around geometry. We're still kind of working to formalize that. So, but it is being talked about for sure.
And Omniverse has a bunch of converters from STEP and other CAD formats to USD and things like that.
Yeah. Yeah. Okay.
But I don't think we've reached out to the community per se. I think we've just done it based on the specification, right, Aaron?
Right.
Yeah.
Just for
thank you for your questions.
Yeah, I was Googling for there was this thing called the NIST or AMRF file format, which had boundary representation and all that. And I came upon a document called using the AMRF file or the STEP file format. And it's all and apparently I wrote it, and it was from 1988 to give you an idea of how this. So we're repeating the same stuff.
Well, one question that came up in the 3D formats as we were preparing for this was I suspect the answer is no, but ask it anyway. Does the CAD community at all, is there any interest with subdivision services like Open Subdiv? Because that is a thing that's come up in both USD and glTF.
Yes, yes, it's a very good question. Not that I know of. It's I don't think it's no, I don't think it's a very common thing to use subdivision surfaces in CAD modeling. I could be wrong, but in fact I asked my colleague Josh to join the call in case I got a tough CAD question. Josh, do you know subdivision services? Are they used much in CAD workflows?
Not that I'm like particularly aware of. No.
Right. Yeah, it doesn't surprise me. Yeah, it wasn't intended to be a trick question.
It's probably just Rhino. Yeah.
I believe there's only 2 or 3 major software makers of CAD software that's really used, like CATIA, and I think I don't remember the names, but there's only 2 or 3.
I think it's quite a lot. SolidWorks, Autodesk, yeah, CATIA. There's new ones, Onshape. It's quite popular.
Ashley or Parvis, do you want to comment on any of our products? I am not aware of them.
Fusion 360 uses subdivision surfaces.
Oh, it does.
Yeah, it does.
Okay, thanks, Ramesh.
Yeah. For what it's worth, ANSYS Discovery also has subdivision surfaces.
I just don't know to what extent they're used. That's no.
Well, they're pretty new for Discovery, so it remains to be seen.
Actually, Alias Studio uses it a lot, and we converted to BREP solids. So
that's one way.
Yeah.
And
I think
Siemens recently announced that they joined the Alliance for OpenUSD.
That's interesting.
Yes, they did.
That's great. Yeah, I think I just heard several motivations for subdivision in glTF. So we still have a couple minutes for the official meeting, and then for any folks who can stay on for water cooler, it's always fun. So I just want to open it back up for questions for David. So David, maybe if I could ask a final question for the official part of the meeting. So you've had the pull request open in the glTF repo for a bit. Any big themes for feedback or questions that you've been getting there?
I've had some feedback. I think it's Peter Rideout. I think there's one company involved in architecture, if I remember rightly, and they're interested in the BREP side of things. It's mainly to do with how things are represented and non-manifold geometry, which is something that I'm don't really want to pay attention to right now, but it might be something that is that needs to be discussed further. Provision for non-manifold geometry, also wireframes as well for like milling and stuff.
Gotcha. Okay, well, looking at the time, it's the top of the hour, so David would like to thank you one last time.